Networking becomes much easier when you stop memorizing isolated acronyms and follow one packet through the system. Imagine a laptop opening a secure web application. The browser creates application data. A transport protocol identifies the conversation. Internet protocol gives the packet routable source and destination addresses. Ethernet or Wi-Fi delivers it across the local link. A switch forwards the frame, a router selects the next network, a firewall evaluates policy and state, and the receiving host removes each wrapper in reverse. That journey is the core of this tutorial. We will use the OSI model as a diagnostic lens, map it to the practical TCP/IP stack, animate encapsulation and decapsulation, walk through addressing and routing, trace a TCP handshake, compare TCP with UDP, and analyze a capture using a repeatable packet workflow. Security is not a separate chapter bolted onto the end. At every layer, we will ask 4 questions. What identity or address does this layer trust? What state does it maintain? What evidence can defenders collect? What boundary should block an unexpected path? The models are not the network. They are maps that help teams communicate. A packet capture is not the whole truth either. It is a viewpoint, traffic observed at one interface at one time, before or after some transformations. By the end, you should be able to look at a failed connection and reason from symptoms to layers, read the important fields in a packet trace, distinguish routing problems from transport problems, and turn network fundamentals into concrete security controls. We will finish with a checklist you can use for architecture reviews, troubleshooting, monitoring, and incident response. The OSI model divides communication into 7 conceptual layers. Layer 7 is application, protocols and behaviors visible to software, such as HTTP, DNS, SMTP, and SSH. Layers 6 and 5 are presentation and session. They describe representation, encryption, compression, dialogue, and session coordination. In real internet engineering, those responsibilities are often implemented inside applications and libraries rather than as clean independent protocols. Layer 4 is transport. TCP provides a reliable ordered byte stream with ports, acknowledgments, retransmission, flow control, and connection state. UDP provides a minimal datagram service with ports, but no inherent delivery, ordering, or duplicate protection. Layer 3 is network. IP addresses hosts and routes datagrams across interconnected networks. Routers primarily make forwarding decisions here. Layer 2 is data link. Ethernet and Wi-Fi move frames across a local link using link layer addresses. Switches learn and forward Ethernet frames within a broadcast domain. Layer 1 is physical, copper, fiber, radio, optical levels, signaling, connectors, and the actual medium. Use the stack to localize symptoms. No link light or excessive radio loss suggests Layer 1. Wrong VLAN, address resolution failure, or a switching loop suggests Layer 2. Missing route, wrong subnet, or expired time to live suggests Layer 3. A reset, retransmission, or closed port suggests Layer 4. A TLS alert, malformed HTTP response, or DNS application error points higher. The pitfall is treating layer labels as rigid truth. TLS sits above transport but influences application identity. VPN tunnels wrap one network inside another. Software-defined overlays create several logical layers over the same physical path. Use OSI to ask better questions, not to win arguments about which box owns a protocol. The practical TCP/IP model is usually shown with 4 layers: application, transport, internet, and link. At the center, each layer adds information needed by the peer at the same conceptual layer. This is encapsulation. Suppose a browser sends an HTTPS request. The application produces encrypted TLS records. TCP divides the byte stream into segments and adds source and destination ports, sequence and acknowledgement numbers, flags, a receive window, and a checksum. IP adds source and destination addresses, a protocol identifier, packet length, and a hop limit or time to live. Ethernet adds source and destination media access control addresses plus an ether type, and the link adds an error detection trailer. The result is nested state, application data inside a transport segment, inside an IP packet, inside a link frame. At a router, the Ethernet wrapper is removed because it was only valid for the incoming link. The router examines the IP destination, decrements the hop limit, selects a next hop, and creates a new link layer frame for the outbound interface. The source and destination IP addresses normally remain end-to-end, unless a device performs address translation. The media access control addresses change at every routed hop. At the destination, decapsulation reverses the process. The interface validates the frame, IP checks whether the packet belongs locally, TCP matches the flow and reorders bytes, TLS authenticates and decrypts, and the application interprets the request. Security controls need the same layered view. A switch port policy cannot validate a TLS server identity. A firewall can block an unexpected destination and port, but may not understand encrypted content. An application gateway can enforce request semantics, but depends on correct identity, routing, and transport beneath it. No single layer can carry the entire security program. A senior troubleshooting habit is to separate names, addresses, and routes. A name answers what service the application wants. DNS commonly maps that name to one or more IP addresses. An address identifies an interface location in the IP topology. A route tells a device where to send a packet next. The sender compares the destination address with its own prefixes. If the destination is on the local network, it resolves a link layer address and sends directly. For IPv4, Address Resolution Protocol commonly maps an IP address to a media access control address. For IPv6, neighbor discovery performs related functions. If the destination is remote, the host sends the frame to a default gateway. The router performs a longest prefix match. The most specific route wins. The selected route identifies an outbound interface and possibly a next hop address. Each router repeats the decision until the packet reaches a directly connected destination network or a route fails. Network address translation can rewrite addresses and ports at a boundary. That means an analyst must know whether a capture was taken before or after translation. The same flow may have different five-tuples at different observation points. Common failures include a wrong subnet mask, missing default route, asymmetric routing, stale neighbor information, overlapping private address space, a security group that permits the forward path but not the return path, and a maximum transmission unit problem that drops packets too large for part of the route. Security recommendations follow directly. Protect DNS resolution and log changes. Use authenticated administrative access to routers and switches. Disable unused interfaces and services. Filter spoof source addresses at trust boundaries. Separate management traffic from user traffic. Document address ownership and routing intent. Log denied traffic, but tune volume so useful evidence is retained. Most importantly, do not assume reachability equals authorization. A route says where traffic can go. Policy must still say whether it should go there. TCP creates a reliable ordered byte stream between two socket endpoints. The connection normally begins with a three-way handshake. The client sends SYN with an initial sequence number and options. The server replies SYNACK, acknowledging the client and proposing its own sequence number. The client returns ACK. Both endpoints now have synchronized sequence spaces and negotiated capabilities, such as maximum segment size and window scaling. Sequence numbers describe byte positions. Acknowledgments indicate the next byte expected. If data is lost, the sender retransmits. If packets arrive out of order, the receiver can queue and reorder them. The receive window communicates flow control. Congestion control adjusts sending behavior based on network conditions. In a packet capture, repeated SYN packets with no reply suggest that the request or response is disappearing, the destination is unreachable, or a silent policy is dropping traffic. An immediate reset usually means a host or middlebox rejected the connection, often because no service is listening or policy is explicit. A completed handshake followed by ATLS alert points above basic TCP connectivity. Duplicate acknowledgments and retransmissions indicate loss or reordering, but the capture location matters. Offloading can create artifacts on the capturing host. Connection teardown usually uses FIN and acknowledgments in each direction. A reset terminates state abruptly. Time wait protects later connections from old delayed segments. From a security perspective, restrict listening services, authenticate management planes, rate limit abusive connection attempts, and monitor unexpected SYN patterns, resets, scans, and new east-west connections. Use stateful policy where appropriate, but remember that stateful does not mean safe. A connection can be fully valid at layer 4 and malicious at the application layer. TCP gives delivery semantics. It does not provide confidentiality or prove the user behind the connection. TCP and UDP make different trade-offs. TCP maintains connection state and provides reliable order delivery. It is a natural fit when an application needs a continuous byte stream and wants the transport to handle loss recovery and flow control. UDP sends independent datagrams with minimal transport machinery. The base protocol does not guarantee delivery, order, or duplicate protection. Applications choose UDP when they can tolerate loss, need message boundaries, want application-controlled recovery, or use a modern transport built over UDP, such as QUIC. Do not translate that into TCP secure and UDP insecure. Neither base transport encrypts application content or authenticates a user. TLS commonly secures applications over TCP. QUIC integrates cryptographic protection while using UDP as its substrate. DNS can use both transports depending on the operation and response. The design decision should consider loss behavior, latency, congestion control, retransmission strategy, path maximum transmission unit, state exhaustion, and operational observability. UDP services need particular care against spoofing and amplification. A request that produces a much larger response can be abused when the source address is forged. Limit exposure, validate requests when the protocol allows it, rate limit responses, avoid open resolvers and reflectors, and implement source address validation near network edges. TCP services must resist connection floods and resource exhaustion. Use sane backlogs and timeouts, operating system protections, load balancers where appropriate, and telemetry that distinguishes real demand from abnormal state creation. The pitfall is choosing by folklore. Measure the application's reliability and latency needs, then define authentication, encryption, authorization, logging, and abuse controls independently. Transport selection is one engineering decision, not the security architecture. Packet analysis should start with a question, not with scrolling. First, define the symptom and observation point. Are you investigating one client, one server, one network segment, or a time window? Was the capture taken on the endpoint, before a firewall, after translation, on a switch mirror, or in a cloud traffic mirror? Second, identify the five-tuple: source IP, destination IP, source port, destination port, and transport protocol. That tuple is the initial flow key. Add time, interface, and direction because the same addresses can appear in many simultaneous conversations. Third, build the conversation timeline. For TCP, find the handshake. Check whether sequence and acknowledgement progress makes sense. Look for retransmissions, duplicate acknowledgments, zero windows, resets, long gaps, and incomplete teardown. For UDP, match requests and responses using application identifiers, timing, addresses, and ports. Fourth, move up the stack. Did DNS return the expected address? Did the TLS handshake select the expected server name and protocol version? Did the server certificate match the intended service? Is the application returning an error even though transport is healthy? Fifth, test both directions. A capture with outbound requests and no replies does not prove the server stayed silent. The reply may be blocked, routed asymmetrically, translated differently, or absent from the capture point. Then compare packet evidence with other telemetry, firewall decisions, router flows, DNS logs, endpoint events, identity records, load balancer logs, and application traces. Handle captures as sensitive data. They can contain addresses, hostnames, tokens, credentials in cleartext protocols, file content, user activity, and proprietary payloads. Limit collection to authorized scope, protect files at rest, control access, document retention, and redact before sharing. The goal is not to collect everything. It is to preserve the minimum evidence that can answer the engineering or security question. Network security improves when intended packet paths become explicit policy. Start with zones based on function and risk, user devices, server applications, management systems, security tooling, backups, development, production, guest devices, internet-facing services, and operational technology where relevant. AVLAN is a broadcast boundary, not automatically a security boundary. Traffic between zones must traverse a control that can enforce and log policy. Write rules as narrow statements: source identity or zone, manage device condition, destination service, protocol, port, business purpose, owner, expiration, and logging requirement. Default deny at meaningful trust boundaries. Permit only the communication the application dependency graph requires. Put public services in a demilitarized zone or equivalent isolated segment. Keep management interfaces off the public internet. Use separate administrative workstations and identities. Require strong authentication for network devices. Backup configurations, protect the backup plane, and continuously compare running state with approved state. Collect visibility from complementary sources. Full packet capture gives rich detail but high cost and privacy risk. Flow records summarize who talked to whom, when, and how much. DNS logs expose naming behavior. Firewall logs show policy outcomes. Endpoint telemetry explains the process and user context behind a connection. Application logs describe semantic success or failure. Baseline normal traffic before writing detections. Alert on a workstation reaching a backup console, a user segment scanning management ports, an unexpected protocol crossing into production, a new external destination from a server, unusual DNS patterns, or outbound volume inconsistent with the service. Encrypt traffic in transit, but do not let encryption erase visibility. Preserve endpoint, identity, certificate, flow, and application telemetry. Inspect decrypted content only where authorized, necessary, governed, and proportionate. Segmentation should reduce blast radius, limit lateral movement, and create useful decision points. If every exception becomes permanent, the architecture eventually returns to flat. Finish with a checklist. For architecture, draw the physical path and the logical path. Show endpoints, switches, routers, firewalls, address translation, load balancers, tunnels, cloud boundaries, DNS, identity, and management networks. Mark where addresses, headers, and encryption change. For every permitted flow, record the source, destination, protocol, ports, application owner, business purpose, authentication method, data sensitivity, enforcement point, logging source, and review date. Remove unused paths and expire temporary rules. At Layer 1, verify power, link, optics, cabling, radio quality, duplex, and error counters. At Layer 2, verify VLAN assignment, media access control learning, neighbor resolution, loop prevention, and port security. At Layer 3, verify addresses, prefixes, routes, next hops, maximum transmission unit, and both directions. At Layer 4, verify listening services, handshake state, resets, retransmissions, windows, and timeouts. At the application layer, verify DNS, TLS identity, authentication, authorization, and response semantics. For security, segment by function and risk. Default deny between trust zones. Isolate management and backup planes. Keep device administration off the internet. Use strong authentication, least privilege, secure management protocols, configuration backups, signed software, prompt patching, and monitored change control. For visibility, combine packet captures with flows, DNS, firewall, identity, endpoint, and application logs. Synchronize time. Baseline expected communication. Alert on new destinations, unexpected protocols, scans, denied bursts, abnormal outbound volume, and connections that cross the dependency model. For packet handling, obtain authorization, minimize scope, protect capture files, restrict access, document chain of custody when needed, define retention, redact sensitive content, and never upload a production capture to an unapproved public service. Finally, test your model. Trace one rail transaction end-to-end. Break one dependency in a safe lab. Confirm the expected alert, the expected block, and the recovery path. This tutorial uses original editorial writing, programmatic animation, and synthetic narration. Copyright 2026 CipherVibe. All rights reserved.